Hello, welcome to another exciting episode of Geometry. In this episode, topic 2.3, Introduction to Geometric Proofs. So at this point, we've proved that girls are evil, and we've proved some algebra stuff. Now we're going to actually do some actual geometry proofs. Now there's proper proof technique, like you wouldn't write a poem without using correct grammar. Proof is the poetry of mathematics. So we have correct kind of grammar, and it's like, how do you know when to use a colon versus a semicolon in a poem? So how do you know when to use the congruent symbol versus the equal symbol? So very similar. So here's you go. Segments and angles are congruent. And we use the congruent symbol. So if I'm ever referencing an angle, I can say angle 1 is congruent to angle 2. Right? I can say angle 1 is congruent to angle 2, that's fine. Let's just say two angles are congruent. You don't want to say angle 1 is equal to angle 2. If you want to use the equal sign, you have to reference the measurements. So you could say the measure of angle 1 is equal to the measure of angle 2. So again, it's like the difference between a colon and a semicolon. How do you just different enough to warrant different situations. So angles are congruent, measures are equal. So let's talk about some good notation and bad notation. Once again, angles are congruent, measures are equal. This would be the bad notation here. You can say that the measure of an angle is equal to 90. You never want to say that an angle is equal to 90. You say that the measure is equal to 90. So the only difference here is the little m. And it's like the grammar of proof. When using algebra properties, you have to use the measurements and the equal sign. So like you would never say 1 plus 2 is congruent to 3. You don't do that. You say 1 plus 2 is equal to 3. Alright, so you can say that lengths are equal. You do not say that segments you say lengths are equal. You do not say the lengths are congruent. You can say that segments are congruent, like that. You can state givens from a picture. So let's say you have a picture. I can state from the picture that 1 and 3 are vertical angles. I can state from the picture that 1 and 2 are a linear pair. So the picture can give you knowledge. And then just keep going on here. You can add lengths. Remember, this is segment AB right here. This is the length from A to B. So you can add lengths. You do not add segments. We're going to stick with angles for the most part. We're not really going to do segments with proofs. There's a COVID gift for you. We're not going to do segment proofs. Alright, so last thing with segments, the length from A to B plus the length from B to C is equal to the length from A to C, the whole thing. Alright, that's the segment addition postulate. Onto the angle addition postulate. If you've got this opening right here, ACB, and you add it to this opening right here, you get the entire opening. So it's very much, these are like the same thing. This is just the segment, and this is the angle. Alright, on to our first real big geometry proof. And once we prove this, then it'll be called a theorem. When you prove something, you can call it a theorem. So it's going to be called the linear pair theorem after we prove it. If two angles are a linear pair, then the angles are supplementary. So here's what this is going to mean. In the future, we can go straight from linear pair to supplementary. We can make that jump. Actually, there's quite a bit of a jump here. It actually requires all of these lines of thought. Our brain goes through that. We just need to slow our brain down and take a look at what's happening. So the first thing we're going to do is we always start a proof with a piece of assumed knowledge. So now there is somebody giving us this knowledge that 1 and 2 in this picture, put a 1 and a 2 there, are a linear pair. So we're going to start with a piece of given knowledge. You always start a proof with a given assumption or knowledge or something. Now, that's what we're working with. We're working with linear pair at this point. That's what we've been given. So now we have to ask ourselves, what does a linear pair give us? What does a linear pair give us? And so turn in your notes to these definitions. And let's go look at a linear pair. This was the last lesson. A linear pair says, a linear pair, if and only if they have a common vertex and make opposite rays. So this is good. What this definition tells us is that a linear pair makes opposite rays. It doesn't tell us that a linear pair is supplementary. It tells us that a linear pair makes opposite rays. Okay, so we can kind of linear pair imply our next statement is going to be that this and this are opposite rays. That's the definition of a linear pair. You can feel free to do LP for linear pair. Abbreviate as much as you want, like I did definition with abbreviation. Okay, so what does opposite rays give us? Let's go look at the definition of opposite rays. Opposite rays, if and only have the common endpoint, and form a straight angle. Aha! Opposite rays make a straight angle. So that's the definition of opposite rays. Linear pair implies opposite rays implies straight angle. What does a straight angle imply? Well, let's go look and see what a straight angle gives us. A straight angle. Straight angle, if and only if it's 180. Okay, so a straight angle implies that the measure of ACD is 180 degrees. So we've got 180 degrees. That's the definition of a straight angle. And now we're stuck. In order to be supplementary, we have to combine these two angles. So now we're stuck here. We're stuck here. And how do you combine two angles? You use this angle addition postulate up here. The angle addition postulate says you can add two angles to make the entire opening. So what we can say is that angle 1 and angle 2 make this whole opening ACD. That's the angle addition postulate. And now what we've done is we have ACD here, and in this step ACD, the measure of ACD is equal to 1 and 2. And we also have ACD here. And in this step, measure of ACD is equal to 180. So in here it's equal to this, and here it's equal to this. And so what's kind of happening is we have that 1 and 2 make ACD, and ACD equals 180. Or let me write that off to the side here. We have 1 and 2 make ACD, and ACD make 180. That's what we have. Can we use the transitive property to kind of skip the middle part and go straight from 1 and 2 make 180? Yes, we can. That's what we did here. We combined these two thoughts together. We took these two thoughts and made this thought. And that's what a proof is. A proof is you get two thoughts together, you combine them to make a new thought. Now this new thought says that 1 and 2 add to 180. That was the transitive property. And then lastly, what does it mean if two angles add to 180? Well, check this out. Where is it? Supplementary angles. Angles are supplementary if and only if the sum is 180. So therefore, because we've shown that these add up to 180, we can say 1 and 2 are supplementary by the definition of supplementary. So we started with a linear pair and we ended up with supplementary. So there we have it. We've made a connection between linear pair and supplementary. And now we don't have to do this thing ever again. We can just say linear pair makes supplementary. On to the next proof. The vertical angle theorem. You've learned in the past that vertical angles are congruent. Now we're going to prove it. So how do you know? How do you know they're congruent? If I sat down and asked you, how do you know that this angle here is congruent to this angle here? You'd say, well, because Mr. Smith told me. Now I'm going to prove it to you. Okay, so we start with the given information that 1 and 3 are vertical angles. And really I didn't even need to give that to you. You could just get that from the picture. That's how we define vertical angles. So 1 and 3 are vertical angles. That's given. Also from the picture, 1 and 2 are a linear pair. Also from the picture, 2 and 3 are a linear pair. I'm going to put given from the picture there, because I kind of used from the picture to find my linear pairs. Next, what does linear pair imply? What did we just prove? Linear pair implies supplementary. So now we can go straight to this. Because these are linear pairs, they are now supplementary. That's the linear pair theorem. Linear pair theorem. And then we know that supplementary means that they add up to 180. That's how we define supplementary. Supplementary implies two angles add up to 180. And now here's my two thoughts. Remember, I've got two thoughts and I'm combining them. So here's what I see. This is informal. I see 1 and 2 make 180, and 180 makes 2 and 3. So I kind of flipped it around, but that's what we have. 1 and 2 make 180, and 180 makes 2 and 3. So you can combine, if they're ever equal to each other, if they're ever equal to the same thing, then they're equal to each other. So 1 and 2, we can use the transitive property, or the substitution property, if you wanted. You could call that a substitution and get away with it. Transitive property, we're kind of skipping 180 here. And then let's do some algebra. What can I cancel off of both sides of this equation? I can cancel off the 2 using the subtraction property. And now I've got that 1, the measure of 1 is equal to the measure of 3. I'm trying to get congruent. We cannot say that the measures are congruent. We have to now convert it using the definition of congruent. Two angles are congruent if and only if they're the same measure. And that works both ways. So because they have the same measure, that makes them congruent by the definition of congruent. Alright, so now what we've done in this proof, we've gone from vertical angles to congruent. So now we have vertical angles imply congruent. And we can use that whenever we want. It's a new theorem. That's called the vertical angles theorem. So to sum up our theorems that we've learned, we have that linear pair implies supplementary and that vertical angles imply congruent. Alright, a couple more proofs. In this scenario, we've got ourselves it says that ray BD is a bisector. Bisector. So we're going to have to go look at the definition of bisector and tell us what that, and figure out what that means. And ABD is 80. So I'm labeling my picture as I go. Alright, so we're going to prove that this angle is also 80. So you're actually making a step in your mind when you do that. So let's go ahead and prove that. So starting off with our given information, put that in there, and you say given. Next, I gave you a hint here. What can you now conclude based off of the definition of an angle bisector? So let's go look at the angle bisector. What can we conclude? Angle bisector. A ray is an angle bisector if and only if it divides a segment into two congruent angles. Okay? So here we've got that bisect implies congruent. So because of this bisector, we can state that these two angles are congruent. We can say angle ABD is congruent to angle DBC. Alright, so there we have it. So bisector implies congruent. Check. Next it says, what can we conclude based off of the definition of congruent angles? So definition of congruent says congruent implies same measure. So we can go from the angles are congruent to the measures are equal. DBC. Now, check. What can I conclude based off of the substitution property? Substitution is look for things that show up twice. So in here, ABD was equal to 80. Here, ABD is equal to DBC. So what can I replace ABD with? I can replace ABD with 80. So that turns into an 80. That stays the same. That stays the same. Okay, so I've proved now that 80 is equal to DBC. What I need to now do is just flip it around so I get my final result. The measure of DBC is now equal to 80 using the symmetric property. Symmetric property. The nice thing about proofs, the first line is always given, first reason, and the last statement is always what you're trying to prove. Alright, so you at least get some points, even if you have no idea what's going on. We're going to skip 2, we're going to go down to 3. Actually, we're going to skip 3, and we're going to go down to 4. This is going to be our last one. Hopefully I can fit it in. Alright, so we get that 2 and 3 are supplementary. That's given information. Go ahead and put that in there. 2 and 3 are supplementary. Now what does supplementary imply? Supplementary implies that the measures add up to 180. That's the definition of supplementary. That's the end of that thought. End of that thought. Now we need a new thought. Go look at the picture, given from the picture. What can we tell about 1 and 2? 1 and 2 form a linear pair. What do we learn about linear pairs? We learn that linear pairs imply supplementary. So linear pairs and make that 1 and 2 are supplementary. The linear pair theorem. Now use the definition of supplementary. What can we say because they're supplementary? We can say that the measure of angle 1 plus the measure of angle 2 add up to 180. And now 180 shows up twice. In this scenario, 1 and 2 make 180. In this scenario, 2 and 3 make 180. So because they're both making 180, that means they're the same. The measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 2 plus the measure of angle 3. Now I can cross those off using the subtraction property and say the measure of angle 1 is equal to the measure of angle 3. Which says that angle 1 is congruent to angle 3. Now 3 and 4 are vertical angles, which makes 3 congruent to 4.